Hey guys, welcome back. So in the last video, we were talking about quicksort algorithm. We said that in quicksort algorithm, in every iteration, we typically try to find a pivot and make sure that all the elements smaller than pivot are on the left side and all the elements greater than pivot are on the right side. And then we do the same thing recursively for smaller set of problems as well until we have processed all the elements. And once we have processed all the element, we get our final answer, which looks like this, which is a sorted array. So I hope you have understood the overall concept of quicksort. Now let's see how does the algorithm for this technique looks like. So the algorithm is very simple. We take the array on which we need to do the processing, first cell of the array, last cell of the array, and then we do some computation till the time p is less than q. So first we do a partition, which is nothing but finding out pivot. So let's say this is our array, and after doing this partition, this is how this array will look like. So it will return us r, which is nothing but the pivot, which is 5 in this case. And it will make sure that the numbers smaller are on the left side, bigger are on the right side. Now once this is done, we again recursively call the same quicksort on rest of the two subarrays. So the two subarrays are this one and this one. So we again do the same thing on these two subarrays. And ultimately we'll get our final answer, which is the complete sorted array. Now what are we doing in partition or pivot? Simple. We take the last element as a pivot and j as the first element. I will be j minus 1, or we can say p minus 1, as j and p both are same. And then we check. If j is less than pivot, then we have to do some swapping, else nothing needs to be done. So that is all about the quicksort algorithm. Now let's see what is the time and space complexity of this algorithm. So first, coming to the partition, here we have some bunch of constant time operations, and since we are having a loop which in the worst case can travel the entire array, hence it will take order of n time in the worst case. So if we add all of them, we get order of n time. So the same thing we have copied over here. Now if we come to the quicksort algorithm, here we have a constant time operation. Here we have a recursion call. So as we already said that in each partition we typically break down the problem into two equal subproblems. Hence, if we assume that the bigger problem is going to take t of n time, the smaller problem are going to take n by 2 and n by 2 time respectively, because they are exactly half of the bigger problem. Now since this is a recursion, we can simply use a back substitution method to find time complexity to this algorithm. So time complexity for this is order n log n. Now in case if you want to know in details how did we arrive at n log n from these numbers, please refer to merge sort algorithm chapter. There we have shown all these things in lot of details. Now coming to the space complexity is order of n, because we are explicitly not using any extra space the way we were doing in merge sort. But since we have a recursion call over here, hence system will internally use a stack which will have a space complexity order of n. Why order n? Because in the worst case, system might have to push all the n elements in the recursion stack and then pop out all those n elements. So space complexity will be order of n. That is all about the quicksort algorithm. Now let's see which is the situation in which we should use quicksort and when we should not use it. Now we should be using quicksort algorithm when we are concerned about the time complexity. So as we have seen, some of the other sorting techniques like bubble sort, selection, insertion sort, they typically run in order n square time. But since quicksort run in n log n time, it is better than them. Now in which case we should not use quicksort? In case if the space is a concern for us, like embedded systems and all, where space is extremely expensive and we cannot afford it, there quicksort will not work out because it uses extra order n space. The other thing is, if we are concerned about stability in the sort, then again we cannot use quicksort, because Quicksort is not a stable sort. It changes the order of the element with the same value. Hence, we should not use Quicksort in those cases. Now, this is where there is a difference between Quicksort and mergesort as far as usability is concerned. Since both in Quicksort as well as mergesort we use n log n time. Space again is same in both the cases. But this is where there is a difference. Quicksort is not stable, mergesort is stable. So we have to choose our sort accordingly depending on our situation. Now let's see, is there any application which today uses Quicksort? So yes, all these languages over here, they have inbuilt library for sorting, and those sorting methods are primarily based on Quicksort algorithm. Fine, so that is all about the Quicksort algorithm chapter. In the next video, let's see the last algorithm technique, that is heap sort.